Yeah, this presentation is going to be very different from Ilya's presentation. It's going to be more technical. I hope not going to put everyone to sleep, and some people still find it interesting. So yeah, I'm going to talk about the protocol and how it handles congestion. So as we know, blockchains all have some kind of capacity limit today, and it is fundamentally a supply and demand relationship. It's pretty simple. If more people want to use the blockchain than what it can handle, then we have a congestion problem. So what are the actual problems when there is congestion? There are quite a few. One is that transactions may become more expensive, depending on how the underlying blockchain handles gas price change and things like this. And also the user experience would degrade because when there are more transactions than the blockchain can handle, then it's natural to think that some transaction will take longer than they would have taken otherwise. And also it might create instability of the network, degrade the network performance, blocks become slower, and also in some extreme cases, the chain may even stall. Okay, so what are some of the ideas to address this problem? One kind of a natural line of thinking is to say, well, if there's not enough capacity, how about we just add more capacity? And this is, I think, a lot of what different blockchains are working on, and sharding is one way to do this as well. So in Nearest model, the capacity of the network scales roughly with the number of shards that we have in the network. So essentially, the thinking is that if there is more demand than what the network can handle at any given moment in time, then there should be more shards created to handle that load. Okay, that sounds very promising, but there is this new problem. In a network with a single shard, it's very easy to think about transactions and when they reach this limit, or like when they reach the capacity of the blockchain. If there are too many transactions, we can just stop taking them so that they don't overflow the network. But with many shards, it's going to get a bit more complicated, and I'll talk about why that's the case. So let's imagine we have somehow 100 shards, and there's this one shard that hosts the near social contract, which is essentially what's behind all the boss stuff that Ilya just talked about. And because it's very popular, everyone wants to use it, wants to interact with it. So there are users on different shards, from shard 1 to shard 99, and they're all interested in using this contract. And even though in each of those shards, the users are not actually exceeding the capacity, or they may even be only utilizing a fraction of the capacity, what will happen is that they will send some transaction from their shard to the shard 0, and internally we call transaction between two shards a receipt. And what will happen is that because all of those receipts are all coming in from shard 1 to shard 99 into shard 0, even though each of them do not exceed the limit of the shard, they would create a huge burden because it's now multiplied by 99, and then shard 0 gets screwed. Yeah, so to recap, we can assume that each shard has a fixed capacity, and the capacity is actually the same across different shards. And it's possible to initiate cross-draw transactions that will spend a little gas in the origin shard and a lot of gas in the destination shard. So even though each shard can locally control the influx of transactions so that they locally don't exceed the limit, globally you can still have very heavy congestion on a hot shard because of those cross-draw transactions. So a kind of simple idea is to say we just don't allow that to happen, right? Whenever there is congestion on a shard, we just say that all the receipts coming from other shards would stop, and we would essentially fail them. It definitely solves the problem, but it creates some other or maybe even bigger problems, which is that now it makes the life of developers as well as users very difficult. For developers, you need to think about the case where some of their transactions just randomly fail in the middle. So let's think about the example, right? Let's say there is a tipping widget on near social where if you like some post, you can give it a tip, let's say some amount of near. And then like users are taking advantage of this feature, and then someone like look at a post they like, they decide to give them like 1 year tip. It all works very well until this near social contract or like the shard it lives on gets very congested, and then some users' tip would fail, and then the receipt just like stop in the middle. Now it becomes a problem because the user might just lose that 1 year if the failure is not handled properly. And also for the users, and it's also a big problem because now they can just see their transactions randomly failing from time to time without actually understanding what happened. And as I said before, they may also even get into some very undesirable state where there's potential monetary loss. So overall, this is not an ideal solution. Another idea that's more promising is what we call limit ingestion. Right? So if we think about what actually happens in the previous case, this shard got very overloaded because it's trying to essentially hold all the requests from other shard on the shard itself. But obviously, it has some kind of limit on itself, so it cannot hold this request indefinitely forever, and at some point, it will get overloaded. So what we want to do is I want to say, well, when the shard itself starts to get overloaded, it should tell other shard that I'm reaching some limit. So the other shard will stop sending receipt to them, and then this kind of pressure eventually back propagates to the end users. And the user would at some point know that, well, the network is congested, I cannot send transactions anymore. This is much better than user like not knowing what happened, send their transaction and then failed in the middle, and then they might end up in a very undesirable state. So more concretely, what happens is that each shard will have an outgoing buffer with limited capacity C. And once the capacity of the buffer is reached, the shard will stop accepting transactions or receipts. And then this process continues on until the pressure propagates to the users at some point. Okay, so let's look at the example. Oh, I guess the animation doesn't work here, but I don't think that really matters. So let's say we have this hot shard with near social contract, and then there may be many shards in the system, but for the sake of this example, let's just say we'll just look at a few other shards. So let's say the user is sending some transaction to shard 2 to call some contract. The contract generates a receipt. You can think it was another transaction to shard 1 that calls some other contract, and then the other contract eventually calls the near social contract, potentially to update some user information there. And what happens when the shard 0 gets very congested is that the shard 1 will know that shard 0 is getting congested, so it's going to put the receipt in the outgoing buffer. And when the buffer becomes full, the shard 2 will know that shard 1's buffer is full, so it is going to stop sending receipt there, and it accumulates its own buffer, and eventually its own buffer will become full, and the user will know that, oh, the blockchain is congested, so I cannot send more transactions. Yeah, so to recap, the idea is basically to only process incoming transactions or receipt when there is space left in the outgoing buffer. Okay, that sounds very nice, but we actually have another problem, which is deadlocking. So let's consider the following case. Let's say there is a system with only 2 shards, shard 0 and shard 1, and they're both full. And in order to make progress, let's say there's only 1 contract on each shard, and what the contract does is essentially to call the other contract, right? So the contract on shard 0 basically calls shard 1, and contract on shard 1 calls shard 0. And to make progress, they each will need to process some receipt, but every single receipt they process will generate a new receipt to the other shard. But now there's a problem, because when they're both full, you cannot actually make progress, because each of them is waiting for the other shard to free up some capacity so that you can process a receipt and generate a new receipt that goes to that shard. There are a few ideas on how to address this problem, and I'll talk about one of the ideas here. So this idea is called cross-shard capacity lending. So if we think about what actually happens in the previous case, essentially it's because it's possible to create this cycle where you're a contract on shard 0, and there's another contract on shard 1, they call each other, they essentially form this loop. And at least in nearest model, it's possible for one receipt to generate multiple receipts as a result of execution. So if we quantify congestion from the point of view of number of receipts, that's just not a very good metric because you can create this like essentially infinite loop there. And the idea behind this solution is to say we want to break the cycle by introducing something that's monotonically decreasing throughout the execution, so that even if you have this like cycle of contract calling each other, what will happen is that this quantity would essentially start to decrease over time, and like every time you run through the cycle, this quantity would decrease, and eventually it would reach 0, and cannot actually form this like infinite cycle that causes you to have this deadlocking problem. Unfortunately, gas is such a function that is monotonically decreasing throughout the execution. What that means is that, let's say you attach some amount of gas to your transaction, and after it starts executing, no matter how many steps it takes, at every single step of the execution, it would consume a non-zero amount of gas. So even if, let's say, you have 2 receipts generated as a result of processing 1 receipt, the sum of the gas attached to both of those receipts will be less than the gas attached to the original one. And then what this idea does is that it decreases the buffer of the origin shard and then increase the buffer of the destination shard according to the amount of gas attached to the receipt that is generated through the execution. And of course, the capacity would be returned back to the origin shard after the receipt is processed. So that might sound very abstract. So let's look at the example. Let's say there's 2 shards, shard 0 and shard 1. And then there's this outgoing receipt from shard 0 to shard 1 as a result of processing some other receipt within shard 0. And it carries X amount of gas. So when this happens, what will happen is that the buffer of shard 0 would decrease by X, and then the capacity of the buffer in shard 1 would increase by X. And here the buffer capacity is measured in gas. So yeah, to recap, basically the core idea is that after processing a receipt, the sum of the attached gas of child receipt is strictly less than the attached gas of the parent receipt. And then by construction, the system is guaranteed to make progress. Okay, that all sounds very nice, but there is another important problem that we haven't touched on, which is priority of transactions. So some users would prefer to pay a higher price to get their transactions in, even if there is heavy congestion. The reason is that what they can gain from doing that transaction, the value they can extract from that transaction way exceeds the amount of money they need to pay for transaction fee. So they essentially don't mind. And then examples including people running arbitrage bots, liquidation, and or like transferring like large amount of value and etc. But it's also a very difficult problem to solve, right? So we thought about building a mechanism to inject higher priority transactions or receipt into the protocol, but that would actually make it extremely complex and hard to reason about. There are several reasons for that. One is that by doing that, we essentially lose any kind of theoretical guarantees on the latency of the transactions. This is because for any given transaction, it is possible that someone would inject transaction with higher priority by paying more. And as a result, you cannot really say like, well, how long this transaction will take at most to be processed and answer questions like those. And also, along the same line, you actually need to figure out how to store the lower priority transactions or receipt, because because in the middle of the execution, some transaction or receipt can be injected, So because you have limited capacity, you cannot process all of them. So some of them would be left there. So you need to figure out what to do with them. Likely the solution is to put them in the state so that everyone actually agrees on what are the receipts that are not executed. But storing stuff in the state is not free, and especially because you don't actually know how long it would take for the network to actually process those lower priority transactions. Essentially, you need to figure out a way to charge users, and how that actually works is also very complex. And there's another question, which is that what if people want to change their priority midway through the execution because they observe congestion that happened after their transaction started? And now you run into this funny problem where, like, in order to bump the priority of some other receipt, you actually need to send a transaction, and that in turn will generate some receipt to bump the receipt. And you need to figure out the relative priority of those two types of receipts and how they interact with each other. And now that's not a problem that we want to be solving because it just involves too many moving pieces, and it makes things very complex. So the idea we have instead is to say, well, we want to move some of that complexity off-chain and actually auction block space instead. So the idea is that we want the protocol to define a way to auction part of the block space as a fast lane or a priority lane, so that people can use that to submit transactions and then get their transactions in relatively quickly by paying more. And then validators or third-party service providers can essentially run the auction for the block space and then provide a service to users who want to utilize those prioritized block space. So one of the thinking behind this idea is that off-chain transaction prioritization is in a way inevitable, because with the MEV stuff, as we all know that it's already happening, and there's essentially no way to actually stop it. So the idea is to say, well, we just embrace that, and also this would allow us to simplify the protocol design compared to the solution where we actually need to implement some auction on the transaction level and actually move the more complex part of chain. Okay, to recap, the congestion problem is much more complex in a sharded blockchain than a non-sharded blockchain. And also the transaction priority problem is also difficult, and we think it's better to handle some of that off-chain. And for the future work, so I talked about some of the ongoing work that we're doing. Not all of them are fully implemented, and in the future we'll focus more on understanding the economic implications of congestion and how to prioritize transaction better. So yeah, that's it for my talk. Thanks, everyone.